lecture, there will be first part on theoretical aspect, I would like to say, and then some other part related to exercise, so to apply the method to some engineering problems.
Alessandra, this is Alberto. I started for you the recording this time.
Okay,
next time you can organize with the students.
Yeah. Thanks. Thank you so much. Okay, so I think after this brief introduction, first of all, I would like to recall you some important aspects related to the exercise. So, as already mentioned by Professor Traverso, in Teams, you have an Excel file with the list of all the students that currently are, let's say, the participants of this course. The exercise that you need to do for the exam need to be performed by groups. So you need to group yourself in groups of 2 or 3 people, not less, no more. So no single person, either no group more than 3 people. You need to group yourself in the Excel file. And the group will perform the exercise. So to perform the exercise, you will not be alone, but you need to collaborate with other students in the same course to perform the exercise. In order that to have a sort of plan and to organize ourselves for the exercise, because you need, let's say, to already done something before the last 4 lecture on the exercise, I kindly ask you to fill in the Excel file within, and just taking the date on the calendar, sorry, within the 8th of October. Then I will write everything also on the chat later. So within the 8th of October, you need to organize yourself in groups and include such information in the Excel file that you can find on Teams. After that date, we will group you by ourselves. So Professor Traverso and me will group you, and you will need to respect such a group for the exercise. So I suggest you to already organize yourself in groups. We know that some of you already doesn't know anyone since you are connected remotely, etc. But we are here, you need to collaborate with the other students. So you already have the emails and contacts of all the students that participate to this course. So please organize yourself in groups for the exercise. And again, the other important things on the exercise is that you need to provide us the exercise at least 1 week before the oral that you will take with Professor Sorge, that has already shown and it's reported in the work plan of this course, in order that we have time to review it before that you take the oral exam with Professor Sorge, and you can, let's say, have the final evaluation of the course as a whole. Related to the slides and the material, I will share during the lecture some slides and material to explain you the different topics. You will find all the materials on Aula Web. So before next lecture, you will find the slides of today and so on for the other lectures. In any case, feel free to write an email to Professor Traverso, and he will forward to me for any question or comments you might have on the topics that I will explain to you, or as a whole on the exercise, etc. So I don't know if there are any comments or questions on this part, which is more bureaucratic and administrative stuff. Otherwise, we can start with this fourth lecture, which is related to a preliminary overview of the uncertainty quantification methodologies, and in particular on Monte Carlo analysis. So just give me, no, sorry, it's not the right one. Now you should be able to see the screen. Could you just confirm me that you can see the slides?
Yes, we can see them.
Yes, Professor.
Thank you so much. So, as mentioned today, I will explain you how it works, uncertainty estimation, and in particular one of the methods to perform uncertainty quantification analysis, which is the Monte Carlo simulation. First of all, I would like to recall a little bit on the different methods that could be applied for uncertainty quantification analysis, that could be, let's say, divided or split in forward uncertainty quantification analysis and backward uncertainty quantification analysis. In the first type of analysis, so in the forward analysis, the idea is that we would like to understand which is the probability of the output, so the probability of our interested value or parameter based on a given probability of the inputs. So we know the probability of the inputs, and we would like to understand how this probability, this uncertainty, affect the output. So just to give you a simple example, we have a probability and uncertainty on the efficiency of a compressor in a gas turbine, and we would like to understand how such uncertainty have an impact on the power output of the gas turbine. This is a forward uncertainty quantification analysis, so from the input to the output. The backward uncertainty quantification analysis is when we would like to obtain the probability of the inputs. So it is an inverse problem that, based on the uncertainty and the probability density function of the inputs that we are able to measure, we would like to understand the probability of the inputs. So this is just a graphic example of what I have already explained on the forward uncertainty propagation. So in general, we always approach the simulation and analysis in a deterministic way. So we have our black box, which is the system, our model, and we have a set of inputs, and through the model we calculate and analyze an output. So with the forward uncertainty propagation, I would like to understand how the distribution of the inputs that we need to set and we need to know from literature data, from the experience of the user, from measurement data, how such uncertainty propagates to an output. And the idea is not only to understand which is the mean and the standard deviation of the output, but also through which probability density function the output data fit. So the idea of the forward uncertainty quantification, which is the most applied one in engineering problems, is first of all to evaluate which are called low order moments of the output, which are essentially the mean and the standard deviation, or the variance. So you know that the standard deviation and the variance are strictly correlated to each other. The second objective is to evaluate which is the reliability of the output. So this is especially important in engineering simulation, where we would like to understand from simulation how and where the outputs of a system are closely related to the performance. So to understand if we simulate the performance of a gas turbine, if we include uncertainty quantification analysis, we can better understand how could be the performance of the system in the real field. So to already estimate which could be the probability and the variation of a particular output when we are going to the field. And if we come back to the example that I did before, if we simulate through uncertainty quantification analysis the power output of a gas turbine based on the probability of the compressor efficiency, we simulate it, we see which is the variation of the power output at simulation level, and then we can go to the field running the gas turbine, and theoretically we already know which will be the variance of the power output that we are able to measure, because we already performed some uncertainty quantification, so we already estimate which is the probability of the different inputs that we have on the system. And the third main objective and motivation behind the uncertainty quantification analysis is that we can assess a complete probability distribution of the output. And this is important, and we will see later in a few weeks when we discuss about robot design, is that we can perform some optimization exercise, optimization problems that taking into account the complete distribution of the outputs and the inputs. So we are able to perform an optimization that consider the different uncertainty that we can have on the inputs, so that at the end the output will be most robust, because it will not be affected by the different uncertainty on the inputs. I will drop this slide. You will see, let's say, it's very comprehensive presentation. You will find it on the HoloWeb next week. I will skip some slides to focus on more the most important aspect of the uncertainty quantification. But of course, you can take, let's say, example or insights of some of the problems and some of the topic that I have not explained you during the lecture to perform your essay for the exercitation. In general, the different forward uncertainty quantification methodology could be classified in two main groups. The first one is what is called as intrusive methods, and the second one is what is called non-intrusive methods. In the intrusive methods, they in general have a very good approximation of the outputs, could be provide a very good evaluation of the probability density function of the outputs, but have two main drawbacks. The fact that this kind of methods require intensive modification of numerical code, so you need to modify the equations that you use in your model to evaluate the output to perform the uncertainty modification analysis. So you cannot use the model as a sort of black box, but you need to modify what is written on it. And the second main drawback is that it requires a lot of runs. So, and we will see later what I mean with runs. A lot of runs to achieve the results of the simulation. But in some way, specifically in the aeronautics sector, they are used because it's easier and it's safe, the achievement of a correct result. The second classification, what is called non-intrusive methods, these are methods in which there is no need to modify the code, so the equation that you use to evaluate the output. So your model, the model of your gas turbine, is considered as a sort of black box in which you modify just the inputs that you give to the model run, and then you collect the output. So the inputs that you give to the model are different, and the number of iterations are different, depend on the different methods that you use, and of course there are different the way that you utilize and use the output of the black box to evaluate the mean, the standard deviation, and the PDF, and the probability density function. But in all of them, the main pro is that you don't need to modify any equation of your model. Among the different uncertainty quantification methodologies related to the forward analysis and related to the non-intrusive methods, there is another classification which is called between sampling methods and approximate methods. Among the sampling methods, we have the main three, let's say, methodology that you can apply, what is called Monte Carlo simulation, that you maybe already know about that or hear about that. We have what is called adaptive sampling methods, which are methods that are based on Monte Carlo, but the number of runs are, let's say, not totally random, but they are in somehow already organized, and you choose which inputs you would like to use for performing uncertainty quantification analysis. And then we have the ANOVA, which could be included in the sampling methods that are based on Monte Carlo, but could provide you some additional information on the uncertainty propagation of the inputs to an output, and also to understand better what the Monte Carlo cannot do, to understand how each input could affect the output of our interest. While in Monte Carlo, if you have 3-4 inputs, which are uncertainty, you run the model, you run Monte Carlo, you collect the probability density function on the output, but you don't know if is the output number 1 or the output number 2 or 3 or 4 or all of them or just some of them have an impact on the output. This could be understandable by applying the ANOVA methodology, so you know if the variance of our interest output is caused by a single input or a sum of them. And then we have different approximate methods. These methods, there are a lot of them on the literature. In the slides I reported just some of them, and in any case during the lecture I will focus more on the response sensitivity analysis because it's the one that you will use in the exercise. That are methods that somehow approximate the mean and the standard deviation, so you cannot reach the exact value of the mean and the standard deviation of the output, but just an approximation of it, because they are based on a limited number of runs to be performed. In general, how the methods work. So in any case, if you are talking about sampling methods or if you are talking about approximate methods, all of them are based on the fact that you will run your model for a number of times, what is called run, and the number of the runs depends on the methods that you use and on the approximation that you would like to achieve. You run the model several times, several runs, you collect the output, and then you will analyze properly such output in a different way based on the method that you use to evaluate which are the low order moment, which is the mean and standard deviation, which is the probability density function. That not always can be analyzed. It depends on the method that you use, and other interesting results, interesting information that you might have from the output. So all the methods work in the same way. You have a number of, you need to identify which are the inputs that are affected by the uncertainty, and then you run the model several times. Just to give a brief overview of how the different models that I have just explained you work, and then we will focus more on Monte Carlo. So Monte Carlo is the simple one because you set the input variable and you sample them with their distribution. So you need to identify each of the input, which distribution they follow, which is the mean and the standard deviation. Then you run the model with the current set of variables, you collect the output, and you are able to evaluate the mean, the standard deviation, and the probability density function. The ANOVA analysis is a way to determine the influence of all the input parameters that you have considered from a series of experimental results, so from a series of runs. So it's an analysis that help you to understand which inputs influence the outputs and with which importance, because at the end you can, let's say, evaluate the variance of the output, how is structured. So the variance of the output will be the sum of the variance associated to each single inputs. So we are able to understand which of the input that you are considering influence more the output. And this, as you can imagine, is an important result because when you go to the field, you can understand better to which input you need to take care more, or you need to know with a more accuracy, because are the one that could affect mostly the output. So just to give you an example, if I know that is the compressor efficiency that affect more the power output of a gas turbine instead, I don't know, of the turbine efficiency, when I go to my manufacturer, I would like to know with more accuracy the compressor efficiency instead of the turbine efficiency, because it's the critical parameter that could affect more the output. So if I know better which is the compressor efficiency, I can trust more on the power output that I will have on the field. The response sensitivity analysis, which is one of the approximate method, is based on Taylor series expansion. We will see in very detail in next week. So the idea is to evaluate the output through a Taylor series expansion of the function using the partial derivatives. In this way, we are able to evaluate very quickly and with a good precision the mean and the standard deviation. Then we have among the different approximate methods, we have also the polynomial chaos, which is a stochastic method which is based on spectral representation of uncertainty in a way that we are able to calculate the system response of a model through the use of orthogonal polynomials. So the idea is to through the polynomial chaos, we are able to say structure to evaluate the output through the sum of the different polynomial, to which the coefficients of such polynomial could help us to evaluate and to calculate the mean and the standard deviation. There are different kinds of polynomial chaos methodology for the selection of the point that you need to use for running your model. That are all of them based on non-intrusive technique. I will not focus on that. They are very mathematical, let's say, way to evaluate the output, but the idea again is to substitute our expensive model with an orthogonal polynomial, which is easier and fast to calculate. And then we have what is called, for example, mid-range approximation method. That is a method used specifically when you would like to perform an optimization under uncertainty. So it's an optimization technique that could help you to optimize your problem, so to find the optimal of our model, of your model, including which is the uncertainty quantification propagation. And again, the idea behind this method is to substitute your expensive model, which take too much time to run, with a meta model, which is again a sort of polynomial of your response. So just to make a summary of the feature of the different uncertainty quantification methodology, and which are the pros and the cons, and then we will focus on the Monte Carlo. In the sampling methods, the simulation is repeated several times in a randomly way, so you not choose the input variable value, but is set randomly. These kind of methods are very large computational, have a large computational effort because you need to run the model with a large number of run, but they are more precise. Specifically, it's easier to have an exact solution, specifically if you have a very nonlinear energy system model, if you are considering nonlinear energy system model. While among the different approximating methods, all of them are based on the fact that the idea behind is to substitute your model with a sort of function that is easier and faster to be run. The function could be based on Taylor series function or orthogonal polynomials or metamodel, but the idea behind is the same. All these approximating methods are very practical, are very fast, need few number of calculation, and when I talk about few number of calculation, I mean several order lower than Monte Carlo simulation to achieve the auto-calculated output, but all of them have the problem that need to be properly set up to calculate the output. If you are not able to properly set up the methods, the output and the results that you achieve with this methodology could be wrong. So you need to take care and have more attention on the let's say parameter that you use, both for the responsivity analysis, for the polynomial cause, for the mid-range approximation method, in a way that you are sure that the results that you achieve are correct. And in fact, it's most of the time in the first simulation that you perform with your model, you always compare the results of the responsivity analysis with Monte Carlo in order that you know that the methods are properly set up, and then you run all the other simulation and the whole analysis that you would like to perform. But it's always a better behavior, a better approach to compare your model with a Monte Carlo simulation, because in this way you are sure that the results that you achieve and you collect with approximating methods are correct. I don't know if there are any questions or comments on this very brief, I would like to say, overview of the different uncertainty quantification methodologies, the difference between the sampling methods and the approximate methods, which are the pros and the cons of each of them. So, if you have
I have a question. Let me ask you about that. In slide number 12,
this one?
Number 12.
12, sorry.
Yeah. Yeah, in this method, it was in sampling, yes. if I'm not mistaken. It was in category of sampling. I have a question. Is that show that which input is directly influence on increasing the output variance?
Sorry, could you repeat a little bit high? Your voice is very low, sorry.
I think you said that input is directly influenced on increasing the output variance.
Yeah, because let's say we will see more in detail next week. While in Monte Carlo simulation, you run the model, but actually you don't know how each input affect the variance of the output. So you don't know if the variance of the output is more influenced by the uncertainty of input number 1 or input number 2. Through the ANOVA, which is strictly correlated, however, with Monte Carlo, you will be able to understand the total variance of the output. You will, let's say, split them in different variants, and each of the variants is related to one single input. So at the end, the total variation of the output will be the sum of the variation related to each single input. So it will be the variation related to input 1 plus the variation related to input 2 plus the variation related to input 3. So at the end, through the ANOVA, you can understand the total variation of the output, how it is composed. So you know if it's more influenced by the variation related to the input number 1 or the input number 2 or 3 or 4 or whatever. It depends on how many inputs you are considering in the analysis. And it's important because at the end you can consider if an uncertainty of one of the input could be somehow negligible, so it's not important because it doesn't affect the variation of the output.
So you mean they are directly, the input is directly just connected to the output. So in this case, we knew which one is directly influenced on the output. So in this case, you see that the influence on the increasing accuracy, yes?
Yeah.
And for the two next slide, I think that was in 14, about polynomial chaos.
Yes.
What is the psi here? It is basis. I don't know what does that mean.
What is the?
Psi.
The size.
Psi x. Is basis.
Okay, sorry. Okay, within polynomial chaos, the idea is to replace the expensive model, which is, I don't know, your CFD model, with an orthogonal polynomial. The orthogonal polynomial is structured with the bases, which are, let's say, specific type of polynomial to be used when you, let's say, when you create the orthogonal polynomial. Okay, it's better. I'm trying to find the slide where maybe it's better explained, so you can help you on that. Otherwise, I will focus a little bit more on next week, because the idea is that you split the model in the sum of different polynomial. For each polynomial, you need to choose the bases, which are standard bases, let's say, and based on the basis that you use, how you will run the polynomial cause is different, and the coefficients that are associated to each basis. And the bases are chosen based on the type of distribution that you have. So if you have a normal distribution for the input, you need to use a certain basis. If you have a uniform distribution of the input, you need to use another basis, which is at the end a type of polynomial. So it's Jacobi polynomial. I know that are very difficult word, but there are different kind of polynomial that you can use in the polynomial cause, and these polynomial are based on the distribution of the inputs. And then you run the model several times to evaluate the coefficients related and associated to each of the polynomial. And based on these coefficients, at the end, you will be able to calculate which is the mean and the standard deviation.
So it means that it is adaptive, yes? Adaptive to the model and
yes.
the distribution of the data. Okay,
yes.
I totally know that. Totally that. Thank you for your explanation. Thank you.
Thank you.